Okay, so let's get started. Any questions before we keep going? All right, so let's do one more example and then we'll start talking about stability of hulls. Ship. Water plane areas. Okay, so we're given water plane level 0, 1, 2, 3, 4, and the corresponding area. 500, 1000. And we're also told the water planes are 2.6 meters apart. WP0 is the keel. WP4 is the design water line. Okay, and with this data, we are told to, 1, use trapezoidal rule. Nabla, if you remember, this is the submerged volume. And KB is keel to B distance. KB, B is the center of buoyancy. So this distance gives us vertical center of buoyancy. All right, and anytime you have a problem, always draw a sketch to orient yourselves. So let's see, let's think about what's given to us. We're given water plane areas, meaning if we have the hull, you basically slice it parallel to the water lines. And 0 is when you slice it at the very bottom, the keel level. The area of the slice that you get is 500 meters squared. You move up from the keel 2.6 meters, and the next slice is 1,000 meters squared. Move up another 2.6, 2,000 meters squared. So it's basically the water plane area keeps increasing as we go up, which makes sense because the hull shape is usually narrower towards the keel. All right, and if we try to visualize this, this would, if we try to visualize those slices, the one easy way is to look at it from the front. If you are standing in front, let's say at the fore of the hull and looking down, well, not looking down, looking along the hull, what would the cross section look like? So this is the z-axis and the y-axis. And coming out towards us is the x-axis. Okay, so you're basically looking along the ship hull towards the aft. And if the hull shape is something like this, and this is the water line. Remember, this is a symbol we use to denote water line. The slices that we get would basically be, slice 1 would be this guy. Okay, so this would be slice number, let's say water plane 0. And area is 500 meters squared. And I've only drawn one half of the hull. Of course, it's mirror symmetric, so we have the full, well, you have the full shape. Okay, let me just draw it. So this is the hull. So that's the first water plane. Oh, well, the 0th water plane. Then the next one is over here. And you keep going, all right? So that's basically the slices that the data is given to us. I've only drawn 3, but the question gives us 5 different water planes. Okay, fine. How do we use this information to how would you use this information to compute the volume? We're given area of the slices, and we're given this guy is what? 2.6 meters. So how would you do it?
We need to know the length of each of those cross sections.
The length? You mean the out of plane length?
Yeah. Mm-hmm.
Okay, so if you knew the length, how would you do it then?
Well, it'd be the sum of the different lengths times their area.
Okay. So, all right. I think, so let's say this is my hull, all right? This is the deck, this is the keel. And that's the fore, that's the aft. So the view we are looking at right now is if I look at it this way, and the slices, the stations basically, that's the cross section that I've drawn. Now think about the water plane. The water plane is if you cut it this way, right? That's the water plane. And that area is given to us. If you slice it that way, the slice you get, that's the area is given to us. If you slice it at the very bottom here, 500 meters squared. If you slice it just a bit above, 1,000 meters squared. Another 2.6 meters above, 2,000 meters squared, okay? So does that make sense, the orientation of the problem? So think about the area. The area corresponds to what? Does it correspond to the shaded thing I've drawn or something else?
I guess the area would be if you're looking at a top view, like if you're looking at from the z-axis down, And you see, yeah, like you're drawing right there.
Yeah.
I guess I guess I was wrong. I guess that area's got the length built into it. So if I take that area times the height, the z-axis, then I should get the volume.
Yeah, exactly. So if you, here we're looking at, let's say, the front view. If you look at the top view, meaning you send a drone that takes a picture from the top, these water plane areas would be, basically that's the keel line, that's the smallest silhouette. And then that's water plane 1 is slightly larger. Water plane 2 is slightly larger. Okay, so there we have basically 5 different water plane slices given to us here. Does it make sense to everybody what we're looking at now? The area from the top view, we've just switched views, so you're standing up here in the fore part of the hull and looking along this way. This view is what that represents. So we're looking at these slices, but from the edge, along the edge of the slices. That's why it's very thin. It's actually out of the plane and into the plane. Okay, does that make sense to everybody? Don't think about the volume, just visualizing the problem first. Are you able to visualize it in your minds? There are 10 people, and tell me, yes, no, maybe. Okay, I'll call you out by name if you don't say anything. All right, Zachary, Zach Barker. Does this make sense?
Yep, makes sense.
All right, Abigail. Abigail? Okay, Chad?
Yes, it does.
All right, Griffin? Okay, Raymond?
Yes.
All right, so it seems to be okay for most people now. If it doesn't, tell me, I'll explain again. It's just water plane areas, that's imagine the slices you would look at. And then this is just 2 different views looking at the same thing. So this innermost slice I've drawn would correspond to this bottom slice here, which of course goes the full length. All right, and imagine we have one flat plank at the bottom and another flat plank right above it. We know the areas of both of these. The volume of the solid enclosed in between, a very crude way to approximate that is you average out the area for bottom face and top face and multiply by the distance, okay? That's one way to do it. A better way to do this is to use integration, okay? So wait, again, let me just, let's again look at this stapler. If I give you the bottom, area of the bottom and the area of the top, and I say, distance between these two is 5 centimeters. Give me the volume of the whole thing. The simplest thing you can do is say, okay, this is an oddly shaped body. I will treat it as a rectangle, okay? And you'll say, all right, I'll just take the area of this guy and multiply by height. That gives you the volume. Doesn't give you the volume of this stapler, it gives you the volume of a box, which you've made some error. You've taken some extra volume, which shouldn't be part of this. It's, if you recall, this is very, this is analogous to what we do in integration, right? We create boxes to make our life easy. And you don't need to create a rectangular box. You can create a trapezoidal box. So that's what when we use the trapezoidal rule, that's exactly what we will be doing. Okay, so the way you would compute the volume here, so nabla using trapezoidal rule is what? Okay, let's see. So what do you say? Well, how? Let's call this A0, A1, A2, A3, A4. How should we write it? Okay. I'm just bringing back one of the older pages. So forget about this too. Look at this. Trapezoidal rule is what? It's distance between the left point and the right point times the average of the two heights, okay? That's the first interval. Next interval is distance between the next 2 points and the average of the 2 points. You do the same thing here. Distance between the 2 points, the first 2 planes is 2.6. And we take the average area of the top and the bottom. So 500 plus 1,000 over 2. Okay? That takes care of the very first block, the 3D block. That, of course, this comes out of the plane. So the block that's enclosed by my pen here. Okay. Then the next 3D block is this guy, top here and here. All right. You tell me what will be the volume of this next section that I'm circling right now.
Be 2.6 times 1,000 plus 2,000 divided by 2.
Yeah, so it's basically, again, we use the trapezoidal rule. The distance between the two areas is 2.6 times whatever the area of the top face is plus area of the bottom face divided by 2. So 1,000 plus 2,000 divided by 2. And you keep going, right? It's the same as what we did earlier. And if you write it just symbolically, it's delta Z times area 0 plus area 1 over 2 plus delta Z times area 1 plus area 2 over 2, dot, dot, dot. So if you write it with the symbols, it comes out to be exactly the same as what we had earlier. Instead of F0, F1, we have A0, A1. Instead of delta X, we have delta Z. Same thing. Okay. So that's how you would compute the volume, the submerged volume, if you're given the water plane areas. Next question is, so that's the first question. Let's write the next question. Okay, use Simpsons rule. To compute, oh, we haven't computed the KB yet. Okay, we'll come to that. So compute nabla and KB. All right. So we already said about how to do nabla, the volume, using trapezoidal rule. What do you change in here to use Simpsons rule instead? Let me bring back the formula. Where is okay, so Simpsons rule was this guy, h over 3, blah, blah, blah. Okay, what should we do now? How should we adapt this? Remember what delta x represented and what F0, F1, F2 represented, and try to apply this here. What should we do? Okay, what's
Z over 3 plus, I forget the formula already, but it's A0 plus 4, A1 plus A2 over, I think it's 4. I don't know. I don't remember the formula right, even though we just saw it.
Okay, so let me write the formula first. So this is H over 3 F0 plus 4 F1 plus F2. All right. So again, H over 3, think about what H represents. It represents the smallest subinterval width. And we know we need 3 points. So we need the bottom, the middle point, and the top point. And for both the subintervals have distance 2.6. So we have 2.6 over 3 times F0, okay? Now we're talking about the area. Area is F0. So A0 plus 4A1 plus A2. That's the bottom 3 slices, okay? So this is the, let me make the slices. So we have slice 0, 1, 2, 3, 4. So this first term represents us taking basically this shade 1, 2, 3. Yeah, this shaded area. Well, volume, since it comes out of the plane. All right, what would you do? We need basically one more expression to cover the whole solid. What would you write next? Plus what?
2.6 over 3 plus A2 plus 4A3 plus A4.
Okay, and the reason we do that is to form the next, this black shaded chunk of the hull, we basically need to take this guy, and this guy. So this is A2, this is A3, this is A4. Okay. All right, any questions about this? We'll do the KB in a second, but any questions about how to compute the volume of a hull? Always visualize what the slices look like, and then make sure you get the arrangement. You're able to visualize the arrangement. Any questions here? All right. So that's just computing the volume, submerged volume. Let's compute the KB, all right? Let's see what the KB means. So to compute KB, again, we use the same view we were looking at. We have Z here, we have Y here, and we have the hull. Yeah, narrow hull, but fine. And we have the water line. K is always, we mark K to be the keel, the bottom of the hull. And B is located somewhere. We don't know where yet. We need to find this distance, KB. All right. And remember, B is the center of buoyancy. What that means is all the buoyant force that's supporting your weight acts at that point. It's vertically upward and it passes through that point. Knowing this is very important because it helps, well, it's critical to a lot of stability computations, as we will see in a bit. So B is, remember, it's the center of the submerged volume. So if you remember, we wrote, well, we can write ZB as Z times dV over dV. This is exactly the same as if you were doing area centroid. Now you're doing a volume centroid. So if you go and look back at the formulas for area centroid, they will look exactly like this, with 2 integrals instead of 3, because you're doing area. Now we are doing volume, so that's why we have 3 integrals. Okay. So this guy, the bottom part, will resolve into basically nabla. This is the volume. The top part would be something a little bit more complicated, but not too much more. And paper. Okay. So just taking the numerator here. So numerator, it's a triple integral of z dx dy dz. Let's see what this dx dy means. So dx dy is basically area of the water plane, right? Look at this. If you have y is lateral direction and x is out of the plane, so moving along the center line towards aft or the fore, it's basically dx times dy represents these same slices that we were talking about here. So that represents dA of water plane. And once you integrate in x and y, all you're left with is integral in z, z times area water plane as a function of z dz. And this is similar to what we did for the area integrals. We simplified the double integral to a single integral first. Same thing here. We simplify a triple integral to a single integral. Z goes from keel to the deck line, to the deck water line. Does that make sense? What we're doing here? If you know this, would you be able to do numerical integration using trapezoidal rule for the numerator?
Yes.
Okay, all right. Other 9 people, please wake up. Do you remember how to do this? Yeah, this is one reason why I really, really don't like remote teaching. If you were here, I could see your faces and I could tell whether things make sense or not. Right now, I'm staring at screen, so no clue. So the other 9 people that are online right now, if you say nothing makes sense, start over, I'll be happy. So say something. Why? Yeah, see, now I have no clue what makes sense and what doesn't. So I don't know what to explain. So please tell me.
I think Tobiah was trying to send a chat about it.
Oh, okay, okay. Sorry, the chat notification doesn't come. I think I remember, but it won't hurt to go over it. Okay, perfect, perfect. So let me bring back notes from the previous class. Let me find it. Okay, okay. Okay, I guess I didn't bring it. So let me take this guy. Yeah, 1 second. I'm just trying to find a good place which we can use. Oh, here, perfect. So this is what we did in the previous classes, finding the centroid, xc, yc. Remember, we did double integral x dA, double integral y dA. And we say, all right, we keep simplifying this, and we end up with this. Xc is the top guy over the area. Look here, it's the same thing. Same exact thing here. Double integral of x dA, when we were talking about xc, x centroid. Now we're talking about the center of buoyancy. So we have the triple integral. Since we are talking about the z coordinate, we have the z inside. Since we have the volume integral, we have a dv instead of a dA. So same thing on top. Similarly, area on the bottom, area, volume on the bottom here, on the right side. All right. So it's the same, whether you do it for xb, yb, or zb, you just replace the z with x or y. Okay? And once we simplified this, the first integral here, that's what we're doing in this step here. We put in the limits and we ended up with, in terms of x, we have to integrate from one end to the other, x times f of x dx. Same thing we arrive at here. Now we are dealing with the z-axis, so z from one end to the other. What does one end to the other mean? So in the z direction, one end is the keel, the other end is the waterline. That's why I wrote the limits here as going from keel to the waterline. But inside we have this thing, look, z times some function. Same as here, x times some function, dx, instead we have a dz. This function in this case was the height of the curve because we were trying to compute the area. But now this function will be the area of the slice, okay? Area of the slice because we're trying to compute the volume. And you see, as we change the z coordinate, as we are at z equals 0, the area is something, versus z equal the waterline, the area is completely different. That is why area of the water plane is a function of z, okay? So this integral is as far as we can go analytically. Now, to go further, we need to change this into a numerical integral. For that, we just need to recall how we changed this guy into a numerical integral. So let's see how we did that. We said, let me see, where is a good example? Okay, this is a good example. So this is the numerator, okay, x fx dx. See how we changed it? Remember we said we would replace x fx with a g of x and then use the same trapezoidal rule as always. So now looking at this guy, can you say, all right, I'll use this approach and form an analogous expression for the integral? What would you write? Is that okay? Does it make sense now? How this is related to what we did for areas? This, again, we're doing the same thing, but in 3 dimensions, so for volume. But all the concepts remain the same. All right, so how would you change this continuous integral into a numerical integral? Just look at this guy here, and what do you say we should write? Oh, wait, there's another chat. Let me check. Okay, that makes sense. All right. So, okay. So take a guess. Just the top part here. Using this information, how do you change this integral into this trapezoidal rule?
Well, for the first one, for z, I would use delta z over 2, or what is that, 2.6 over 2. And then for the second one, I would probably use 2.6 plus half of 2.6. And then for the area, I would use the area 0 plus area 1 divided by 2.
0 plus area 1. Oh, okay. I think you're trying to deconstruct that bit. There's an easier way. Look at this. X times some function. You have a z times some function. So how would you write this right-hand side equivalently for the z guy? Instead of x0, we write z0. Instead of function 0, we write area 0. Okay? And plus. Same thing, okay? So, well, the other way we talked about was you replace this whole thing with g of z. Once you do that, you have an integral of g of z dz. If that is easier for you, that's perfectly fine to do. And now you can use trapezoidal rule for this. So trapezoidal rule is, you get dz becomes delta z, g0 plus g1 over 2 plus delta z, g1 plus g2 over 2 plus dot, dot, dot. Okay. And this g, we said it's z times a. So we can just replace this g0, it's delta z, z0, a0 plus z1, a1 over 2 plus dot, dot, dot. Okay. So just go back and review your notes and you'll see this is exactly the same thing we did for the earlier problems. Just in 3 dimensions. Nothing, concept-wise, nothing changes. All right, I'll leave the Simpsons rule to you since, again, this is analogous to what we did Simpsons Rule in 2D. Once you do the homework, hopefully this will become much clearer. And yeah, you have to go through it. Yeah, because we did all of this last class, but it's easy to forget. Okay. So take a look at the homework and ask me, email me questions you have, or we can again discuss it on Wednesday. It's due on Wednesday night. That stuff will be covered on the quiz, so make sure you understand it. All right. Let me check if there's anything in the chat. No. Okay, so that's basically all of all that we need to know about integrating, because as you see, it's the same in 1D versus 2D versus 3D. If you get the concept down, then you're done. And this approach is basically what all the software you use, they all do this. Of course, they don't just use 5 slices like we're doing here. They use hundreds of slices, but that's easy to compute for them. It's just addition and multiplication. So not a lot. It's not a very difficult thing to do. Of course, the computer will not have these areas given to it, the water plane areas. How would you compute the water plane areas? How would the computer do it? How would the computer compute these water plane areas or your 3D hull model that you have put into the program?
Well, the computer must have an analytical model of your Y versus your X at each Z location.
All right, so you're saying the computer must need to know the analytical expression for the curve of the water plane. But it doesn't. Remember, that's exactly what we did in the previous class. All the computer needs is, okay, at this coordinate, this again is the top view of the water plane. What's the lateral distance to my hull from the center line? And once you know that for all the different points, you can compute the area numerically. So that's exactly what the computer does. Another option, of course, is to form a fit, analytical fit to all of these points, which is not, it's not necessarily the best option because it can create weird numerical issues. So the easiest thing to do is compute the water plane area using numerical integration. Once you do that for all these different levels, then you can compute the volume, again, using numerical integration. So all of this, the same thing, basically, you combine. Not just for area and volume, but for every property you need, like the moment of inertia and the metacenter height, which we'll talk about right now. All right. So make sure you have all of this numerical stuff. You understand all of that well. If you do, the rest is very easy. Okay, so hydrostatics. Okay, we talk about buoyancy and stability. All right, let me write a statement and then we'll talk about this. So a floating body A floating body is upright and it gets, let's say, it inclines a little bit because there's a strong wind blowing from one side. What happens once the wind dies down? What's going to happen?
Well, hopefully it's going to restore itself to its equilibrium position, but it'll probably overshoot and come back and oscillate.
All right, so that's one thing that might happen. So once the wind dies down, the tilted body comes back to its original position. It'll bob about a little bit, but it should be fine. That's not the only thing that can happen. If the shape of the body looks a certain way, the wind will push it up over all the way and it'll roll over. All right, so think of very wide boat in heavy seas. No, okay, think of a very wide hull ship. There's a lot of wind. It might roll or heel a bit because of the wind, but once the wind dies down, it comes back easily. Now think of a very narrow canoe. And if there's a very strong wind, it'll flip over, all right? Let's assume the canoe is sticking out of the water sufficiently. So there's many possibilities that can occur, and we think in terms of equilibrium, whether it's stable equilibrium, it's unstable equilibrium, or it's neutral equilibrium. So one case is where we have, let's say this is a bowl. It's a bowl, not a hull. And we have a ball sphere that's rolling along the sides of the bowl. This is what constitutes stable equilibrium. Why do we call it stable? It's because the sphere or the ball rolling along the sides of the wall wants to stay at the bottom here. If we nudge it a little bit, so if we displace it slightly, it'll oscillate about that position. And slowly it'll come back and be at rest here. Okay. Now let me turn the bowl upside down and put a ball on top here. Now it's easy to see if you give it a nudge, that's unstable equilibrium. Why unstable? Because there's no way the ball is coming back to the top once I give it a nudge. All right. And the third one is neutral equilibrium. Do you remember how we can draw the shape? So the ball is in neutral equilibrium.
Be just a horizontal line.
Yeah, a flat table surface. So this guy. And you put your ball on a tabletop and you nudge it. If you nudge it, the ball just moves and stays at the new position. So that's why it's called neutral. It has no tendency to come back or go further. It just stays at the new location. All right. And for the same equilibrium concepts apply for hulls, ship hulls. If we have a hull and if we nudge it a little bit and it wants to come back and become upright, it's in stable equilibrium. If the hull gets nudged a little bit and immediately flips upside down, that's unstable equilibrium. In very rare cases, what might happen is you have the hull and you nudge it, it tilts a bit and then stays at that position. That's very rare, but it can happen. All right, that's called neutral equilibrium. And we'll see how the way we design these hulls results in each of these cases. All right, so stable equilibrium for a free floating ship. The thing that oh, not stable, static equilibrium. So if a free floating ship is, if you say it's in static equilibrium, that means there's no resultant force or resultant moment acting on it. If there is a net force acting on it, an unbalanced force, the ship will no longer be in equilibrium. If there is an unbalanced moment acting on it, no longer in equilibrium. The ship will start either pitching or rolling or yawing, depending on what axis the moment is acting about. So equilibrium means, static equilibrium means resultant of all forces and moments acting on the ship must equal 0. Okay. The resultant, that's an important one. So for instance, if you have a ship, or let's say if you have a small boat and you tie it to the dock, okay? So let's say the line is attached here, and you're running the engine. So you're basically trying to move that way. So the engines provide thrust that way, but the line is creating a force backward. The net force is 0, so your hull stays in place. If the line is cut, then the net force is not 0 anymore, so you start moving forward. Okay, so when talking about these forces, different types of forces acting on the hull, the first thing that pops up in mind is, okay, the weight of the whole ship, which includes the weight of the hull material, any cargo you're carrying, the fuel you're carrying. So all of that, the total weight is called the displacement of the ship. So let's draw a front section. So this is just a very simple shape that represents a cross section of the ship as one of the stations, okay? And here we have the water line. The weight, the entire weight of the ship acts at the center of gravity, the G, okay? So that's where we have all this downward weight acting. Remember, we also call this displacement. So weight. Now, remember we talked about who's balancing all this weight. So it's the buoyant forces. And those buoyant forces act at this point. let's call it F buoyant. Okay. And if you're in equilibrium, the upward buoyant force will exactly be balanced by the downward weight. And when the ship is in water, from fluid mechanics, do you remember how the pressure changes with depth? What will be the pressure here compared to the pressure here?
It would be rho GH.
Okay, rho GH. And let's say there's pressure at the water line is 0. Of course, the absolute pressure is not 0, it's atmospheric pressure, but we only care about the gauge pressure. So this varies linearly as we increase our depth. Okay, perfect. On the bottom face, of course, the hull is very complex. So what I'm drawing is will not be exact. But at the key level, you get a constant pressure pointing upward. Okay. So this pressure distribution is responsible for the buoyant force. That's the source of the buoyant force. You see, the left side pressure distribution is exactly balanced by the right side. So that's the two lateral sides of the hull, the starboard and port. They balance each other exactly. If that were not the case, your hull would start moving sideways. And the pressure on the bottom is actually what gives us our F buoyant. So this is force distribution. Due to hydrostatic pressure. All right. So that's a very basic picture of the forces acting on the hull. At static equilibrium, we know that the resultant force has to be 0. So the buoyant force is exactly equal to the displacement. Okay. And the displacement, well, is exactly equal to rho g nabla. So this is displacement. That is submerged volume. And I mean, this should make sense intuitively. If your weight is higher, your submerged volume increases. So they both have to go up for the equality to be valid. Rho doesn't change, G doesn't change. Rho is rho seawater, G is 9.81 meter per second squared. Okay. So this basically means that this implies the resultant, which is sum of all forces, is equal to 0. Force vector, one is negative, one is positive. So the sum will end up being 0. All right, now let's think about one slightly different scenario where instead of having our G located at the center line, we say the G is somewhere over here. What will happen in that case? How can, first question, how can you make that happen? Instead of G being centered, you have G somewhere near the edge. What practical scenario can you think of that happens in?
You're not evenly loaded.
Okay, yeah, so on the deck, you put a huge cargo container on this side. Okay, so you've basically moved your center of gravity to here. Now think about what this does. So the weight is no longer going through the center line. It's going through this new point, imaginary point near my pen here. What does this do? This weight pointing downward.
Creates a moment.
Okay, it creates a clockwise moment. Okay, you see this pointing downward and the buoyant force pointing upward. That's basically creating a torque or a couple. And that's what will cause your ship to tilt clockwise. So we know all of this intuitively. If you place a heavy weight on this side, the ship will heel a little bit clockwise. And it'll do so up until a point where everything becomes balanced again, okay? So what does that mean? So it'll tilt until the new G and the B are in line again. So the new position of, so basically the weight and the buoyant force are balanced perfectly again. And at that point, it'll stop. So it'll tilt a bit and it'll stop. And we'll see exactly how much will it tilt? How do I make sure it doesn't tilt over all the way? All right. And we'll use all of the things we've talked about. The area moment of inertia is useful for computing that. The centroid, the center of buoyancy, all of these are, we need to know to be able to compute those things. So static equilibrium also means that the summation of all the moments is equal to 0. And in this case, that's telling us that xb has to equal yb, xb has to equal xg, and yb has to equal yg. See, if I displace this guy sideways, that's me changing yg. If I move the G out of paper, that'll create a pitching tilt, okay? A list, and the ZG, of course, is not equal. You see there's a separation between the Z axis, Z coordinate of B and Z coordinate of G. That's okay. That's actually essential to keep it this way. So the moment sum is equal to 0, which means these two things are true. And let me just specify that xb and yb are coordinates of center of buoyancy. And xg, yg coordinates for center of gravity. All right. And to talk about all of this, the stability of a hull, there's a few specific terms we use. So the first one is called initial stability. Initial stability. when somebody asks you about the initial stability of a hull design, they're asking you, what's the behavior of the hull if it's perturbed in its equilibrium position? Okay, so initial stability conveys the behavior of the ship in the neighborhood. I'll tell you why I'm writing in the neighborhood. So in the neighborhood of its position of equilibrium. Okay, meaning what happens if we perturb the equilibrium position by just a little bit, by a little bit. Right, let me just do this 1 second. So let's say this is our equilibrium position, our hull is upright. If we perturb this just a little bit, so tilt it just slightly. What the initial stability is asking the question, what happens? Okay, so see now neighborhood, because I'm no longer in my original stable configuration, new configuration. Not very far off from my initial configuration. So that's why we call this initial stability. And of course, you can say the hull is neutrally stable, or it's in stable equilibrium or in unstable equilibrium. But we will learn how to quantify all of that. You give me a number that tells me, all right, the hull is very, very stable, or it's barely stable and it'll go unstable at any moment. All right. And to quantify that, we talk about another term called the metacenter. And this is defined as the intersection of the center line Okay, I've just underlined it to separate out the two lines, basically. Center of the hull is one line, and line perpendicular to the water line is another line. But this line should also pass through the center of buoyancy. I'll draw a sketch and it will become clearer. All right. So we will basically draw a hull that's fully upright at first. And then the same hull is tilted over slightly. Let's say the water line is over here. And for this guy, hey, remember the water line will stay horizontal. It's just the hull that's tilting. All right, so let's draw a few things. First, we have the keel. We have the center of gravity somewhere, the center of buoyancy somewhere. All right. And let's look at where we would locate the meta center. So it says the intersection of the center line of the hull. So let's draw the center line of the hull. That's the center line. With a line perpendicular to the water line. In this case, the perpendicular line is, again, a vertical straight line. Okay, and it has to pass through the center of buoyancy, so same here. So basically, our two lines coincide. So the meta center M would be located somewhere on this line. We don't know the exact location yet. We will learn how to compute the distance between M and keel. Okay. But all we can say right now is the meta center has to be located along this line. What happens when we tilt the hull a bit? Let's redraw. Our keel remains the same since it's a geometric thing. You have not shifted any cargo, so G remains the same. This was the original location of the center of buoyancy. Now something different, something is slightly different. So first, center line of the hull, again, is a geometric property, remains the same. So that's the center line. Okay, now let's think about what happens to the center of buoyancy. Remember, buoyancy is the center of the submerged volume. What have you done here when you tilt the hull? Have you increased the submerged volume? Have you decreased it? What have you done? Don't think mathematically, just intuitively. What has happened?
Well, the volume should be the same because your displacement, in weight and so forth is the same.
Okay, so does everybody else see what he's saying? He said the volume doesn't change. Why does the volume not change? The volume of the submerged part of the hull. Okay, so others, do you see why volume won't change? Yes, maybe, no? The submerged volume is the same between these two cases. Why? Why is that? No, okay. All right, so the volume doesn't change because the weight of the hull has not changed. You've just tilted it slightly. You know the weight has to be balanced by the submerged volume. So the same submerged volume here as here, okay? But what have you done is here, the submerged volume was distributed equally on the starboard side and the port side, on the left and the right. What has happened here? So somebody else, what has happened here? Intuitively. If we cut the hull into half, the left half and the right half, what have you done by tilting it over? Is the volume on the right side, the submerged volume, the same as what it was here? Have you increased it or decreased it, or is it the same?
Not the same. Like the left side has more displacement than the right side of the cut.
So you're talking about the left half?
Yeah, when you tilt it, the left side will displace less volume than the right side of
Okay, so you're saying the left half is displacing less water compared to the right half. Okay.
intuitive.
Sorry, I couldn't hear you.
That's what I see. I could be wrong though.
No, that's correct. What you said is correct. So when you tilt it, the left half is basically, you're bringing some of it out of the water, but you're pushing some of the right half down into the water. So you're increasing the volume submerged on the right side, but you're decreasing the submerged volume on the left side. Overall, they're exactly equal and opposite. So the amount you submerge has to be equal to the amount that emerges. The reason it's because the total volume submerged has to be the same, because the weight is the same. But as soon as you do this, you change the volume distribution, the submerged volume distribution. You have moved the location of this center of volume. Just imagine you cut out a volume from here and you glue it over here. So you're basically changing your center of volume so it moves slightly to the right. So this guy will move slightly to the right here, P prime. All right. And so definition of metacenter. One, it has to be intersection between center line, that's our black dashed line, and another line which is perpendicular to the water line. So perpendicular to the water line, and it has to pass through center of buoyancy. So it has to pass through here and it has to be vertically up. Okay. So this would be perpendicular to the water line. And that intersection point is called new metacenter. Yeah. So by definition, the metacenter is always directly above the center of buoyancy. The center of buoyancy moves a bit, but the metacenter will always be perpendicular, vertically above. All right, we're out of time, but next class I'll show you how to compute these distances and how much things move. All right, so make sure to try the homework, and remember we have quiz on next Friday. Any questions? Okay, I'll see you next week.